Welcome to installment 11.5C in our Circuit Protection Fundamentals video series. Today's topic, EFuse versus Polyfuse. On the left side, we have the EFuse, represented by our USB power switch. On the right side, we have our Polyfuse, represented by a piece of polysilicon. So our EFuse has an I limit, which is programmed at the factory or programmed as part of the design. And this current limit is typically in the 20 to 30% range for the small integrated USB devices. And it's very fixed and stable over temperature and over time, and it's very repeatable from device to device. In the event of a short circuit, the EFuse will shut off typically in 1.5 microseconds or so. It's a wide temperature range, and as you can see, as our current ramps up, we hit our threshold and the output voltage drops to 0. It actually works like a current-controlled switch. If the current gets too high, it turns off. The Polyfuse, on the other hand, is temperature-based, and it doesn't actually shut off in response to a high current. Instead, the resistance just increases. I don't know how well you can see on this slide, but across the bottom we have temperature, and on our vertical scale, it's a log scale in resistance, or ohms. And as our temperature increases, we hit a knee, and all of a sudden, boom, the resistance goes up. This will reduce the current going to the load and presumably protect the load and protect the supply. Now, it doesn't shut the current off, it just reduces it. These are thermal devices, so there is a lot of resistance in the Polyfuse to create the heat to get the temperature up to this point. After the device cools down, the resistance will drop again, presumably down below the trip point, and the load can continue to function normally. Now, each time the Polyfuse trips, when it comes back, the resistance is just a little bit higher than it was when it started. Now, here we show some of the effects of this resistance and temperature sensitivity of a Polyfuse. We have 4 curves on this chart. Curve A is a standard thin film fuse, and you can see at low temperature, we're maybe 15% high in our current limit, and then at higher temperatures at 90 degrees C, we're about 30% low. So if you're going to run at high temperature with a thin film fuse, you must derate by at least 30%. With our flat pack fuses, cartridge fuses, a lot of the standard fuses we're used to, there's still some temperature derating, but it's not nearly as steep, maybe 10% high at minus 60 C, and we've got, I think 10% low at plus 120 C. And then we look at the Polyfuse. You can see the Polyfuse has a very high current limit at low temperatures, and then a very steep slope for derating, and at plus 90 C you've got to derate at almost 60%, and that's on top of what is already a very sloppy tolerance. Now, curve D in red, these are our EFuses, and you'll see there really is no temperature derating. They are internally compensated, so they know what the current being delivered to the load is at all times, and they will limit load current to that level. So one big advantage of an EFuse over a Polyfuse is temperature sensitivity, or lack thereof. They also, EFuses will shut off a whole lot faster than a Polyfuse in response to a short circuit or an overcurrent. A couple of stories from the trenches or the lab. We had a particular customer who was testing data cards in a slot, and they were using EFuses. They plugged in the data cards and then put a short circuit on it, and unfortunately the power buses in the data cards not very robust, and they burnt up before the EFuse would actually do its job. So they put in some USB power switch eFuses. The problem went away. They were very happy. Another customer was making set-top boxes, and they had a USB port protected by eFuses. And damage wasn't done, unless you consider brand damage, but they'd plug in a short circuit to test it, and the Polyfuse protected, but it allowed the bus to droop so much that the set-top box processor was resetting. And so every time they ran this test, it would reset. They decided that wasn't acceptable and that would make for a lot of unhappy customers. And they put in a USB eFuse switch. The problem went away. It is the nature of many of these devices that they don't get designed in until somebody's felt some pain. So the Polyfuse summary, well, on the downside, they're slow, they're lossy, almost 2 times as lossy as a regular fuse. They are totally thermal devices. They are very inaccurate. Each overcurrent event does increase the resistance. They're really not suitable for high temperature due to the extremely high temperature sensitivity. And if you do run them at high temperature, they become even more lossy because of the increase in resistance. The benefits of a Polyfuse are they will reset after an overcurrent event, they are low cost, and they can provide compliance with safety regulations. And that is the eFuse versus Polyfuse story. Thank you very much.